This one? It's on? Okay, folks, welcome to the EECS Colloquium. It's my great pleasure to welcome back our dear, very, very dear friend, Christos Papadimitriou, who has disappeared from our lives for a few years, but we are fortunate to have him back. I could give the long formal introduction with this whole list of awards that Christos has, but I think we all know those awards, so I will give you the more fun intro. He literally is the most interesting character in computer science that I've had the privilege to interact with, because in addition to books like on optimization and computational complexity, he has also written novels. Okay, and in those novels he even has sex scenes. Okay, and comic books and various other things. But Christos is truly the Renaissance mind, because he has moved around virtually every area of computer science. I mean, always there is his home base. His home base is theory and computational complexity. But with that, he has gone and dabbled in control and in databases and in information retrieval and of course most recently in AI and neuroscience. But before that, he actually spent many years trying to fix game theory for the game theorists. So I have a cousin who's in economics, and I said, "Have you heard of Christos Papadimitriou?" "Oh, of course, of course, of course." So my stock went up when I said I knew Christos Papadimitriou. Okay, and then he worked in evolution and contributed to this grand puzzle of why is there sex, and now, of course, he's going to tell us about language. Without further ado, Christos Papadimitriou.
Thank you very much, Jitendra. So I'm really delighted to be back. Thanks for coming. I want first to tell you that whatever is true of the hyperbole that Jitendra introduced me with, literally all of it I owe to Berkeley. Okay, so I'm delighted to be here. Okay, it's very inspiring and brings tears to my eyes. Okay, so it's great. Thank you. Let's face it. Okay, AI is still far behind brains, okay, and in several dimensions, okay. And here are, I believe, the 5 right ones: groundedness, okay, so it barely knows about how the world is like; inventiveness and ingenuity, okay, so coming up with very original ideas; continual learning, okay, so sometimes it has to forget to tell dogs from cats in order to learn flowers from plants; emotional social intelligence; and of course the brain works on 16 watts. Okay, so that's a huge one. By the way, how do I know all this? Okay, I found out the old-fashioned tough cop way. Okay, I interrogated AI until it confessed. Okay, so I decided to be done with the obligatory ChatGPT joke early in my talk. Okay, right? So all right. So here's an idea. Since AI and brain seem to be excel in different dimensions, how about if we implemented artificial neural systems that are more brain-like? Okay, so how about if we tried less artificial intelligence? Okay, for what do I mean? Okay, I can't give you a long list, but here is one: no back propagation. there is silence in the room. Okay. Yeah. Don't take my back propagation away. Yeah. Okay. How about that? Okay, that's, why not try to come up with artificial intelligence that works like the brain works, right? And now you realize that you are in huge trouble because you have no clue how the brain works. All right? So, here is a depiction. This is cognitive science. This is experimental neuroscience, okay? And admire the gap, okay? There is a huge gap, not only of scale, so 10 to the 11, but also there is a gap in scientific tradition, scientific methodology, mindset, and so on. I mean, there are two very distinct fields. I mean, these are two amazing books that seem to be parallel universes. They barely reference one another. Okay? So, nobody has put it better than my hero in this business. This is Richard Axel. And 5 years ago, he gave an interview to Neuro magazine, and that's what he said. We do not have a logic for the transformation of neural activity into thought. I view discerning this logic as the most important future direction in neuroscience. Okay? So basically, in order to do what I want to do, which is create a more a less artificial intelligence, we have to solve this problem. Okay? And I find this. I mean, when I saw this, I mean, Richard Axel is 2 floors above my office at Columbia Neuroscience. I mean, he got a Nobel Prize in 2004. And when I read this, I felt that I was blessed by the Pope. Okay, because that's what I have been working. I mean, and I find this an amazing, very surprising statement for at least 2 reasons. First, Axel, who is the most conscious experimentalist that I know, so very, very fanatically sort of Ramon y Cajal type, okay, very, very experimentalist, and don't talk to me about theories, uses the word logic, which to my mind is, evokes a formal system which is eventually computational. Okay? So that's a surprise to me. That was a huge surprise to me. Number 2, the second surprise is that only I and my friends seem to be working on this. Okay? And I'm very interested to see, to meet people who also are interested in this problem. Sometimes it's called the bridging problem. How do you bridge cognitive science and neuroscience? And so, what kind? How could that go about? And here is my plan. Okay, so I want to come up with a mathematical model of the brain. Okay, such that it models reasonably well spiking neurons and synapses. And by simulating this model or by proving theorems about it, you get cognitive phenomena, real cognitive phenomena. All right, and this is my plan, and this is what I'm going to show. This is the story I want to tell you. Okay, this is what I've been working for the last, I guess, 8 years. All right, so I'm going to present you the neural model. I'll call it NEMO now. Okay, and it's a mathematical model of the brain. Okay, so pay attention. Not many talks have such a slide. Okay, mathematical model of the brain. All right, so what is a brain, really? It's a finite number of brain areas. Each has, let's say, for simplicity, the same number, huge number of excitatory neurons, spiking neurons. All areas are recurrently connected by random synapses. Okay, in other words, 2 neurons in every area, they have the same probability of being connected in either direction by a synapse. Now, we know that that axon, that the synapses between neurons are not random in the GNP way, sort of, completely independent way. In fact, there are famous papers that have essentially this as the other title, okay? But we are okay. We have simulated the same ideas with different kind of randomness, local randomness, and so on. And we get, or much more realistic types of neurons, and you get very similar results, very similar behaviors, okay? Is this clear? And also, we have some pairs of these areas are also connected by random bipartite graphs. Is this clear? So basically, it is a directed graph, if you wish, and it's so far we have defined a directed graph, nothing else, okay? And every node has a loop. Is this clear? Cool. Now, how do neurons spike? Neurons fire in discrete steps, okay? That's already a spoiler, okay? Because we know for sure that neurons don't fire in discrete steps. But, as I told you, it is a strong assumption. It's an incredibly simplifying and helpful assumption in mathematics and in simulation. But I believe it's not a distortive assumption. The reason I know it is that we have simulated, we have done the same experiments with more realistic neurons, with sort of the latest type of realistic model neurons, and with plasticity that is much more complicated than the one I'm going to explain, and still you get the same behaviors. Okay, so we don't have much sort of guilt about this assumption. Next is another major simplification. So, to explain, I want to make this as simple as possible. First of all, because that's the kind of guy I am, and second, because I want to simulate it and prove theorems about it. Okay. Each one of these. Okay. There are 5 areas here. Okay, in each one of them, typically in our experiments we have 24 areas.
And you said each node is in a loop.
No. What I'm saying is that in every area there are internal connections, internal random connections, and some pairs of areas have also connections. So any neuron here and any neuron here have a probability of being connected also. And we call these fibers, the red arrows. This is just normal recurrent connectivity that we know that neurons have. Thanks for the question. Any more questions? Yeah.
In terms of the boundary of the system, where, in which direction would I see an optic nerve coming in? With say,
you mean where is sensory, the sensory cortex live?
And in corporeal sense, very highly structured.
Yeah. So, okay. So the question is, how about vision, okay? How about it, okay? So, no. Here is my answer, okay? I have a good answer to your question, okay? So, brace, okay? There is no dearth of people who study vision. Okay, so since Hubel and Wiesel, neuroscientists have been studying vision. Okay, so that's great because it's a fantastic subject. Okay, the point is that if you look at Nobel Prizes in neuroscience, okay, the first ones were given for understanding what neuron is, what synapse is, what neurotransmitter is, and so on. All the rest were given to people who studied the sensory cortex. Except for one exception, which studied almost the sensory cortex, they were studying place cells and grid cells, okay? In other words, neuroscience is a field which really pays a lot of attention to vision. In the human cortex, 95% of the cortex is not sensory, not motor. Okay, it's something else. It's called association cortex. And I want to study this cortex. Okay, so, all right. I mean, so I get this question: how about vision? In every talk I give. Okay, well, I'm not. I don't worry that vision will be left unstudied. Okay, so that's why I'm studying this. Okay? Yeah. Okay. Is this? I mean, did I answer your question?
That's the purpose of this talk, yes.
Yeah. Right. Okay. Good. So I mean, I have to explain what my demeanor on this. Okay. Good. So. It's bipartite GNP. No. I mean, so in our experiments we have to vary it for various reasons. Okay, but yes, I mean, for this model, let's say they're all the same P. And for our theorems, it's always the same P. Okay, so now I'm coming to a crucial point. Okay, when will a neuron fire? Okay, and here is the rule: a neuron will fire in an area. Okay. Will spike when it is one of the k out of n. So think of n as 1,000,000 and n as 1,000, about the square root of n. Okay. So in this area where something has happened in the previous step, the neurons that will fire are the k neurons in orange in this picture, which are the ones that receive the highest synaptic input from the previous step, from the same area or from other areas. Does it make sense? And this models local inhibition. Okay, so you know that a large minority of neurons in every area, they do the job of making sure that not everybody fires and we stay at 16 watts. Okay. And this is a very schematic way of, a very sort of stylized way of modeling this. In reality, what happens is that there is an antagonism between inhibition and spiking, and even after a damped oscillation, it sort of it ends up in this equilibrium of K. And I just telescope to this. Okay, I don't study the transient. Is this okay? I'm delighted you're asking questions. Okay, another little detail, important detail, is that some areas no neuron will spike because these areas are sort of inhibited, and I'm going to tell you the mechanism for that. Okay. All right, we're almost done. Finally, plasticity. Okay, I told you that I'm not going to use backpropagation, I promised, okay? So what am I going to use, okay? What the brain uses, which is plasticity. What's plasticity? It is how the brain learns. Plasticity is basically rules whereby the synaptic ways change. And we have the very simple sort of, the model T of plasticity, which is that if this neuron spike, what Hebb predicted in 1949, if this neuron spikes, and the next step, this neuron spikes, and presumably this was part of the cause why this spikes. I mean, in other words, this is a heuristic for causality. Then this must be an interesting, useful synapse, and therefore its weight is increased. Okay, and in our we just have a parameter beta, which is like 5%. It's increased by 5%. All right. So and that's it. Okay. There is no other rules except for something that I'm going to tell you about how areas are inhibited or disinhibited. Okay. This is the so it's a model that is based on plasticity, randomness, and selection. If you think about it, these are the three forces of life. Okay, typical parameters are this. Okay, so we have n in our simulations in the million or tens of millions. K about 10,000, P is 10 to minus 3, and beta is 5 or 10%. Okay?
Sorry, what was the P?
P is the density. What's the probability that a synapse will exist? Okay, so basically every neuron in an area is connected to 0.1% of its neighborhood. Yeah.
When you say the weight of the synapse is multiplied, what exactly do you mean by weight in this case?
It's a real number. It starts at 1.
Okay, but what's the significance of the weight? If the weight is higher, what does it mean?
Okay, it means the following. Okay, thanks for asking this because that's important. That in the next step, when we calculate what is the synaptic input of every neuron, we multiply by the weight. Okay, this neuron must have fired, so we add the weight of this synapse. So a synapse that has fired has more influence. Okay, can more easily make a neuron fire. Thanks. Is everybody? Yeah.
Since this evolves over time, what model or notion of time do you have? Perfectly discrete?
Perfectly discrete. Yeah. Yes, exactly. Perfectly discrete. As I said, this is a gross simplification, but it's a useful simplification, and it's not distortive. Now, once you have that, the next step function is fully defined. Okay, so if you know who fired, you will know who fired next, and who fired next, and who fired next. Okay, so that's a dynamical system. Okay, and the simulator is available online if you want. So basically, it's interesting. In order to run it, you have to type load brain, which is a fine thing to type first thing in the morning. Okay, and here is the point that the emergent behavior of this dynamical system is assemblies of neurons. Okay, what I mean by it has a a family of very strong stable attractors, which are called assemblies. Okay, and I'll explain exactly what they are. If you want to have a computational analogy, right? If you think about it, that's a very messy dynamical system, and it's the assemblies that enable it to compute. Okay, very much like if you think about the chip, is a very messy dynamical system of silicon atoms and copper atoms and electrons and God knows what else, right? And the reason we can compute is because it has these stable attractors called bits. Okay, and we're in business. Okay, so it's the same way with mind model and assemblies. So what are assemblies? Assemblies is another thing that was predicted by Hebb when he had no right to predict it. What they are large and densely interconnected set of excitatory neurons in the brain area, whose near simultaneous firing is tantamount to the subject's thinking of a particular memory, concept, person, name, word, episode, etc. Okay, so a lot of people believe that they exist. Okay, and they will look for it, but the technology only matured at the beginning of this century for neuroscientists to catch the brain on the act of firing assemblies. And then once Harris and Buzaki was one of the discoverers, Justo was another, and now we see them, we manipulate them, we create them, we forget them, and so on. When I was at Berkeley and I was working on this, I was thinking, I had doubts, self-doubts. Okay, but are they for real? The last 5-6 years, there is, I don't believe there is doubt remaining. Okay, that this is. Everybody believes that assemblies exist and they're a big part of how the brain works. Okay, so incidentally, Yuri Buzaki calls them. He has written a beautiful book called "The Brain from Inside Out." Calls assemblies the alphabet of the brain. Okay. The assemblies have, besides their stability, have some interesting behaviors. I'll start with projection, okay, which is the most basic behavior. So let me explain what it is. Imagine that you have an assembly, and here, and I'm going to copy this assembly here. I'm going to create a copy of this assembly here. That's called projection, all right? How am I going to do it? This assembly fires, and according to the rules, and since there is these random connections here, there is a random distribution of synaptic input on the other side, okay? All right? So it's basically a Gaussian. So if you take the k tail of this Gaussian, this is going to be a number of 1,000 of k neurons, and these k neurons will fire. So this is sort of the proto copy, the first version of the copy that I'm going to create. Okay, but now this assembly spikes again. Okay, and of course the blue assembly spikes also. And now the game has changed. There is synaptic input going this way, but there is also recurrent input. So the blue assembly creates a second wave, a second additive, how do you call it, Gaussian, okay? And now the first Gaussian has slightly increased by 5% because there is plasticity, okay? So it's a complicated phenomenon. And now who is going to be the winner? Not the same. There are going to be some other lucky ones, okay? And it's going to be like that. I mean, they overlap a lot, okay? For a large range of parameters, is about 50% overlap for this first one. But now I go at it again. And the same thing is repeated, and now you have fewer new winners and fewer new winners. And after a dozen, for a very large range of parameter spikes, you get a very stable top copy, okay? Which is very stable in many senses, okay? First of all, it is very dense interconnected, okay? For example, between neurons in the same assembly, the probability of connectivity is not p, is 2p or 3p. Okay? In other words, I have chosen a very dense subset, which, if you think about it, you're a computer scientist, that's a difficult computational problem. How does the brain do it? Okay? So that's a beautiful question. Also, because they have worked hard, these synapses have high weights, okay? And third, if this assembly ever fires again, this will fire also, okay? So they're copies, okay? And now this can have a life of its own. It can be copy itself in a couple of other areas, and then things will start happening, okay? And there are hundreds of other assemblies playing the same game, and you have a complicated dynamical system, okay? A complicated set of attractors of this system, I should say. Other behaviors are reciprocal projection where the copy can make the original spike association if two stimuli happen together, co-occur, or are similar, the corresponding assembly, the corresponding projections move closer and they start overlapping more, okay? Pattern completion, that if you fire like 5% of one of these assemblies, they are so dense and stable that the rest of 95% of the rest of the assemblies will fire, and so on. Merge, okay? You have ways not to copy one assembly, but to create a copy of two assemblies in one, and this is how you can start creating trees, okay? Because this one can be the internal node of a tree that you created, okay? Sequence recall, okay? That's something that we discovered very recently, that if you present a sequence of stimuli, okay, then a sequence of assemblies of copies will be created. But now, if you make the first assembly fire and you wait, the second assembly will fire, the third assembly will fire, because these assemblies have created sort of implicit synaptic connectivity between them in the direction of time. And I believe that this is how, this is one of the mechanisms that the brain uses to keep time. And actually, you can create a fine MNIST classifier with assemblies, okay? All right. Finally, and that's, I swear this is the last part of the model, but very important, long-range interneurons, okay? What are they? Friend Peter Dayan told me not to call them long-range interneurons because there is a bunch of neuroscientists that don't believe in them but believe they're spiking, sort of excitatory neurons. So if you want long-range neurons, okay, what they're in populations extrinsic to the areas, these green populations here, which go and inhibit or disinhibit other areas, okay? Go to remote areas, and these are the control elements of the computation that I'm going to, so far we had just the variables, okay? And now these are the control elements. So basically this, and also they can be recruited by the assemblies of an area. So this area, its assemblies, if they play their hand right, they can recruit this, and every time they fire, they are going to disinhibit this, and this is going to disinhibit this. So they are going to inhibit this area. Okay, so this is a very important part. In fact, there's a beautiful paper by Ruwe Busakic where they have a computational experiment where basically they demonstrate that without LRIs, you cannot have computation. For them, computation is the gamma rhythm of sort of about 50 hertz, 50, 60 hertz of the low gamma rhythm of the brain. And the LRIs constitute the program of the computation, okay? So what I want to tell you is that assemblies and LRIs give you universal computation. That's a Turing-complete language, Turing-complete hardware language. So it can do arbitrary computation with square root of n over k bits, okay? Square root of n over k is about a few dozens, okay? So what it can do, let's say, is computation with 40 bits, which is the same as saying they can simulate any Boolean circuit about the number of gates, but the depth has to be 40. This is a lot of mental computation. This is superhuman mental computation. Okay? Okay. So one of the things we like to do with NeMo is to simulate it. And to simulate these steps of the model, if you do it naively, one needs Pn squared t. Okay? And this is a lot of time. Okay? T is seconds times 50 because we imagine that we are working in 50 hertz time. But we have a lazy simulation technique, and it reduces this to pk squared t squared. So instead of n, we have p here, k here. And, but instead of t, we have t squared. Okay, so this is a 10 to the 4, a 10,000-fold speed up, and it allows us to simulate a few seconds of brain time on a laptop. Okay, so why is this t squared? You see, because you must know this from life. If you are lazy, the things you have to do every day accumulate, right? Yeah. So that's the idea. Okay. So that's 6 seconds sounds like a small, and it takes us a few hours to do 6 seconds of brain time, but it's enough for some cute cognitive phenomena, and that's what I'm going to show you. Yeah, exactly. We're making some extra assumptions or that are implicit. For example, when we have, then we start from another virgin brain, and hope that it's not going to touch much the parts of the brain that we have. Okay, and our simulation is, even the fast lazy simulation is a probabilistic approximation. Okay, but we have checked it that is very accurate. Okay. Yeah. So LRIs are the easiest part. Okay, we only need small populations of neurons there. The LRIs basically inhibit or disinhibit other areas or LRIs. Okay, so basically they set up. When the intention is that when an assembly fires, it has recruited LRIs, and these LRIs are going to set up the brain so that this assembly can do the right thing in every area. Zero code. That's it. I mean, so you have only stimuli, thanks, okay? You only have stimuli and hardware, nothing else. Okay, there is no code, zero code. I mean, sort of, 3 years ago we had code, okay? And people were asking, how is it created? How is it loaded? How is it executed? And so on, right? I mean, but no. So it's just this hardware language that I'm presenting. Now there is nothing else, nothing up my sleeves. And we start only with pristine random synapses, nothing else. Okay, we don't pre-program anything. All right. So remember, next we want to show you how to implement cognitive phenomena. Okay, so for example, I'll only talk about 10 seconds about that. In last year's EECS AAAI, we had I told you, okay, in order to do less artificial intelligence, you have to start to the beginnings of artificial intelligence. How much the beginnings? That much, okay? You are going back to the blocks world, to Terry Winograd's blocks world, and basically you see a block setup, you imagine another block setup, and you want to output basically robotic commands, okay? Put the red block on the table next to the blue block, then put the yellow on top of both, okay? So you want to be able to do this, and we have an EMO setup that does exactly this. But I really want to talk to you about language, okay? So how many of you study language? Okay, so then you know more than the rest of us that language is by far the hardest thing that any brain has done. Okay, So why am I saying that? Imagine what's happening right now. Okay, I create waves in our shared space, and these waves hit your tympanum, and eventually your auditory cortex. And let's not worry about that, which is a miracle in its own. But then they excite representations of words, and they create trees, they create hierarchies, they create parse trees in your brain. Okay, and if if I'm very lucky, you are going to remember these representations as long as you live. Okay, so especially if I say something as stark as this. Okay, all right. So and so I believe. Okay, here is why I'm studying language. It's the hardest thing that any brain has done, I believe, and more to the point, it has evolved over only 3,000 generations. In the same brain. We have the same brain that we had 3,000 generations ago. Okay, so the brain mutations from the chimpanzees. I bet you that none happened during this time. Okay, and we have the same brain changed only by selection, and as a result, what was the fitness of this organism that evolved? Okay, of language. Its fitness is that it is easy to learn by babies, okay? So basically, it has encapsulated, it has captured all features of the brain, of the human brain, okay? So, so it should be the first thing that you should study if you want to understand the human brain. And what I'm going to show you is that, we created last year a parser of English implemented by spiking neurons. Okay, so this is the language organ. So it's Broca's area, Wernicke's area, the lexicon lives here, and so on. Okay, so so here is the architecture of the parser. You have several areas. Okay, I'm showing you 5. We have like a dozen, and they are labeled by by syntactic roles, okay, like object, preposition, adjective, subject, verb, and so on. You have a lexicon where all the words you have learned in your life are here, okay, have representations. And the point is that, and there are also fibers that connect the lexicon and these areas together, okay? And we know that, in the region where we are talking about, in these circles, there are evolutionarily new fibers, okay, that didn't exist in the chimp. So, what's the input? It's a sequence of excitations of word assemblies, okay? So we imagine I mean, we could do a voice recognition trick, but we don't, okay? We imagine that the input is an excitation, sort of, of the word assemblies. We assume that phonology has been solved. Each word assembly has an action set. Its inhibit or disinhibit actions implemented by LRIs. It encodes its part of speech, its syntactic role. So every word, okay, the word cat, when it's executed, it has recruited some LRIs, and they do some work for it. And these LRIs that it has recruited is a characteristic of its syntactic class, of its part of speech. It's a noun, okay? When word assembly fires, the action set is executed. And what can you call the sum total of the word action sets? This is the grammar of the language, okay? I have no better word for it. All right? So let's parse cats chase dogs, okay? It starts this way. Why it starts this way? Why is this stupid fiber disinhibited? It's disinhibited. I mean, here I assume that you disinhibit fibers. That's not an important sort of change in the model. So why is this fiber disinhibited? Because this is English, and you know that you are going to see the subject before the object. Okay, so this is ready to recognize the subject, and indeed this happens, and there is a projection. Okay, so of the cats because it's excited, it automatically projects it in the right subject area. Then chase comes, and immediately what happens is that after the projection of cats, these two open, and that's because we know that we are going to see the verb before the object. Okay, so basically the chase is executed, and now these two fibers open. Why? Because the lexicon knows that chase is a transitive verb, and therefore we'll see an object. Okay, if it was, I don't know, walks or run, then there would be no such thing. And finally, dogs. The object comes, it's projected, and it's done. Okay. It's a justified question. And how do I know that this was parsed, right? Okay, here's the answer. So what does it mean for this device to correctly parse a sentence? And the idea is the following. After the input cats chase dogs, you have a bunch of high synaptic weights, which basically sketch a valid dependency tree. And these synaptic weights, you can actually see them by experiments. Okay, you can run an experiment and you can run a test experiment, a test phase, and see that's what we do. Readout. So and it tells us yes, it has the right dependency tree. Okay, so it's a dependency. It does correct dependency parsing. And in fact, it does a valid, how do you call it, basic parse tree, which is sort of these 5-node. But I'm not going to talk much about it. In any event, so what I want to remind you, is implemented exclusively through the spikes of stylized neuron. Okay, of course, no back propagation. Okay, I have to repeat this. Okay, it uses about 10,000, more than 10 million neurons, and about near 1 trillion of synapses. And this is sort of a much very slow neuromorphic computation, but it's more powerful than Intel's Loihi, for example.
Christos, can I ask a question?
Yeah.
There is always ambiguity in parsing.
Oh, absolutely. Yeah.
And so how is the ambiguity represented? And
Yeah. So basically, what our parser will do? We have run it on ambiguous things. It will make a default guess, and then it will punt if it says that it was a wrong guess. There is, we could, one of the things that we plan to do and we have not done yet is to have a backtracking. Okay, so okay, when was this decision, the wrong decision made? It's not. We have in our paper. This was published in Tackle. It had 20 things that we needed to do. We have done like a dozen of this. Okay, but not sort of. How do you call it? Garden path sentences and the backtracking. Yeah, great question. So it parses simple sentences like this: the young couple in the next house saw the old little white car of the main subject quite clearly. The speed is about half a second of brain time per word. This is about how fast I'm speaking. We also have running simple parsers. We did a Russian parser. Others did Japanese, Hungarian, and Mandarin. And we published in Tackle, presented in ACL 22, and you can find the code online. So before you ask your questions, let me tell you what people ask here. All right, so, but now we have parsers who can do so much more, okay? Yes. It's the world's, it is the decade's worst parser, I realize. However, the point of this parser is that it's biologically plausible. It's implemented exclusively through the spiking of neurons without backprop. It's the first of this kind, and and notice, the last sentence is of importance. We don't see the limit, okay? We do not see how much, what is the limit to how much we can improve it, okay? We add to it once in a while. Every time an undergraduate wants to do a project, so they implement something else, and it's sort of it becomes better and better. Here's a question that unfortunately a reviewer without how do you call it, rebuttal opportunity asked, how are you going to test your theory on humans, okay? And that was obviously a neuroscientist, and I'm sure that he was very pleased with themselves, okay? That they came up with this devastating question, okay? So, and here's my answer: we will not, okay? That's not a theory; it's a proof of concept, okay? So it's an existence theorem that can be done, okay? So I'm not saying that brains parse this way. I don't think that brains parse this way, okay? So having said that, both in the parser, but especially in what I'm going to talk about next, we have taken a lot of pains to agree with what neurolinguists think about the language organ, at least to the extent that there is a consensus about something. Okay, so wherever there is consensus, there is in surprisingly many places, we have implemented this. Okay, so so here is the killer question. Okay, so the truly devastating question. Okay, your parser works. Okay, but how do these things get in place? Okay, how do the labels, subject, object, verb, okay, get in place? How do the words and their action sets get in place? Okay, this is cheating, right? Right? How many of you were about to ask this question? Yeah. Okay. Okay. That's yeah. So all my life I was obsessed with clever proofs. Okay, so now I really dig clever experiments. Okay, and the great thing about experiments is that a bold experiment entitles you to ask a forbidden question. Okay, those of you who are students of language, you realize that this is a blasphemous question. Okay, you are not supposed to ask it. Okay, at least not without a voice that is oppressed by awe. Okay, so is this the natural basis of language? Okay, or something like that. But I ran the experiment and I have the right to ask it now. Okay, this could be the basis of okay, and the answer is no, no way, because the hard part is filling the blanks. It's answering the question that Doris would ask. Okay, so what's the this could be a neural base of language. All this, but without the labels. All right, without the pre-installed words, plus hardware for semantics and hardware for generation. Okay, you want the baby to speak eventually, right?
Vision after all.
Sorry, yes, yeah. We are coming to vision. We are coming to vision. Finally, yes, right. Yeah. And plus the ability to learn all these things. Okay. And so this is what I'm going to present you. Okay, this is what I'm working on now. We want to do biologically plausible language acquisition. Okay, so we are going to start with the hardware very much like this, except there it's going to be a tabula rasa, nothing, of randomly connected areas, fibers, and populations of LRIs, nothing else. Okay, in other words, something that any decent developmental system could deliver to the baby, okay? To the baby brain. And the input to the system, that's the experiment, the input will be a modest amount of grounded, shared attention natural language. This is all very important. Grounded means, grounded is scary. Grounded means in the real world, okay? So it looks like I have to model the real world. Don't worry, okay? Shared attention is important, okay? The tutor and the pupil must know where the other is looking, okay? So, they must have a common sensory background, okay? At this moment, that of the articulation. And what is modest, okay? Modest is a nod to Chomsky and his famous poverty of stimulus. So what? And I now understand what modest means. I have a mathematical definition. It should be a small multiple of the size of the lexicon. If you think about it, you cannot do it less than that, because for every word you must hear it somewhere, and it shouldn't be much more than that. And right now we are playing with something like 10 times like that.
Why not? Why shouldn't it be more?
Because then we go to ChatGPT territory. Okay, we are going to.
But children learn. So the number that I read was 1 million words. They hear 1 million words a month.
Okay. This is very exaggerated. Yeah. So
no, they don't learn 1 million words. But
yeah. So yes. So long discussion. So this is very controversial. This is very controversial. Not very controversial. Factor of 5 controversial. Okay. Yeah. Okay. And the output should be a mature language organ, complete with a lexicon, a comprehender, and a generator. What's a comprehender? A comprehender is a parser that also understands the semantics. Okay? So what's the status report? We have implemented the acquisition of a simple natural language with only intransitive verbs. Okay? So there are no objects. This is a trivial thing to fix, but we have our hands full. Okay? I don't know why I made this decision, but we wanted, I don't want to worry about objects now. Okay, so only transitive verbs. We assume, as with the parser, that phonology has been solved. So we have learned the presentation of nouns and their semantics. We have shown learn representations. We have implemented learning of representation of verbs and their semantics. Incidentally, you only have object nouns and action verbs. And abstract nouns and abstract verbs like peace and mediate are not. I know. I'm sure that that will not be the wall. Okay, that will stop us. We end when the baby, around the 20th month of life, says "daddy gone." Okay, basically says the first full sentence, two-word full sentence. Okay, and implicitly you have to learn the word order of the language, of course. And we are working on the hard case. We have solved the hard case, which is the following: learning syntactic roles of words from overheard language. Okay, modern parents do single word tutoring. Okay, but we know that. How do we know? The greatest example is migrant children. Okay, so 7-year-olds who go to school, their parents don't speak it at home, they only hear it, nobody speaks to them at school, and yet they learn perfect English in 2 months. Okay, so still grounded, of course, and with shared attention. And that's difficult because of the following. Okay, so if you have here is the difficult part, and why I'm saying this is a hard case, because if you hear dogs run, okay, if the baby hears dogs run, because this is the kind of sentences they hear in our experiment, they have no way of knowing that this is English and therefore dogs is the animal. They see a dog running, but they don't know if this is English and dog is the animal, or it's Swahili or Irish, and the dog is the verb. Okay, so they must learn this. Okay, so this is the tricky part, and we can do that. So how do we represent semantics? What do you read there? Yeah, this is the Jitendra slide. Okay, so basically, so how do we represent? There is a different lexicon for nouns and different lexicon for verbs. This is slightly controversial. Okay, it's 80 to 20 controversial. There is 20% of psycholinguists that don't believe that they're separate. There is something called phonology, an area called phonology that contains a representation of the phonemes. It has very strong synaptic connections with the symbol or lemma assembly, which is sort of the symbol for the word dog. That's the only symbol in the whole thing. Then, this symbol has synaptic connections with assemblies in the semantic areas. The main, for objects, the main one is vision. Okay? So it has a very strong connection with vision, which is probably a place in IT where a prototypical dog has been learned. Okay, but there has weaker connections for motor, for olfactory. I don't know, for affect. I love dogs. I fear dogs. So it has. And in our simulations we have these two main areas plus a dozen other semantic areas. Okay, and this is how we represent semantics. The semantic representation of words is a star of assemblies. Okay, verbs is very similar, and sort of So I'll go very fast to the end. The assemblies of the star, their size and overlap. So this is something that I want to. I promised you at the beginning that this way we are going to learn new. That we are up to learn new modes of learning. To find out new modes of learning that are not backpropagation. Okay, and here is something, right? The assemblies of the star, their size and overlap, the strengths of the synaptic connections to the symbol. All are dynamic and encode the meaning of this word for this speaker at this moment. Okay, so this is in other words, it tries to do a very accurate embedding of what this word means. They reflect co-occurrences of words, statistical regularities, order statistics, and changing word context. So, okay. So, by the way, the representation, suppose we can also do multilinguality. That's not a problem. That's easy. We can also do interrogative mode, declarative mode, and so on. I mean, mood. So we can do many other things that I'm omitting. What I'm going to say is that this is a bit reminiscent of word embeddings. For example, the man is to woman as king is to what in our system is answered automatically. Okay, in Word2Vec you had to do a subtraction and a next nearest neighbor search. Here it's automatic because man in lex is connected to assemblies human and male, and queen is connected to royal female. Okay, so this will be when I ask this brain. Man is to woman as king is to what? Queen will come up. Okay, immediately. The next assembly to fire will be queen. Also, I saw the giraffe with my binoculars will be disambiguated correctly. Okay, I didn't see a giraffe that is munching on my binoculars, but I see the giraffe. Okay, cool. In any event, we have just begun. We have just yet to perceive fundamental limits. Our goal is to create in the context of language brain-like hardware that can support various modes of learning, one-shot and few-shot learning, assimilating experience, statistical regularities and patterns, all through Hebbian plasticity. Okay, last slide. Okay, as Jitendra was kind enough to say, I mean, I have invaded other areas in the past, but I've never climbed the hill as steep. I mean, and Bruno so held my hand in my early steps. Okay, so and also for language. Okay, so it's an incredible fascination to work on language. I find so. And basically, this is your payoff, right? That when you do experiments on language, so you really get to ask incredible questions, okay? And we have made progress, and as again, I don't see fundamental limits. So I'm positive that within the next 6 months, I'm very hopeful that in the next 6 months we're going to have a very a good language organ. So, big question. Are we in the right, so basically, sort of, neuroscientists tell me, yeah, okay, so, that's fine. That basically follows the basic tenets of neuroscience. But the brain has so many other things, okay? It has 10 kinds of plasticity that we have discussed, and maybe next year it will be 11, okay, and so on. And the point is, I want to find out how far I can go with this, okay? For plasticity especially, I'm convinced that plasticity is very important in intelligence. But sort of, I don't want the multiplicity of modes of plasticity in the brain, I believe, is incredibly crucial in our intelligence. But I want first to find my first wall on this, okay? Something that I cannot do. Another question, is the design of neuromorphic intelligence systems a useful complementary path to AI? Okay, these are both bets. Here are my collaborators. Santos Vempala, we started with this 10 years ago. Max Dabaja is his student. Mike Collins, my colleague at Columbia now at Google, and Dan Mitropolsky. He's doing all the work, and he's a brilliant computer scientist. He's also a great theoretician, but he's also a fantastic programmer, and he's graduating next year. Okay. Thank you very much.
You told us about the importance of the LRIs.
how exactly did you pick and place the LRIs in your model, and where did they come in our current brain? Is that something that was always there, or did that happen in the last 3,000 generations and evolve?
Yeah, yeah.
manner?
So, I mean, I don't know that anybody has found LRIs near the language, so in the left brain here. So, where, I mean, I was talking to a great neuroscientist at Tübingen, and Peter Dayan, and he told me, don't bet on LRIs, call them something else, okay, because there are so many ways that you can implement this, okay, who knows how they're implemented, okay, and so, because I'm a Busaki fan and Busaki likes LRIs, sort of, I did it as a nod to him, okay, so I call them LRIs. But, there are many ways that you can implement such control mechanisms, and we know they exist, okay, so, we know that such things happen, okay, yeah, thanks. Thanks, Carl. Yeah.
So very interesting, Christos. What does your model do without
inputs? When it sleeps. Yeah, great. It hallucinates. Okay, it starts doing random things.
How much do you let it hallucinate? So I mean, if you run these experiments, are you always putting inputs in, or?
So we freeze it between inputs.
What would happen if you would
Yeah, great question. So we have not. Yeah, that's fantastic. I mean, it will probably replay. It will probably and so on. I mean, it will do things like.
Better or worse?
Great question. We haven't tried. Yeah, you understand. So that our brains don't do well if we never sleep. Okay. And we know that from experiments that animals between trials, so they think about what happened, okay, and that's learning is that's important part of learning. Alyosha.
So, I think this kind of connected to the previous question a little bit. So, in the beginning of your talk, you kind of posited the primacy of algorithms over data. You said, forget vision, who cares, the input, right? But then, toward the end of the talk, it seems like data is seeping in. So, what is your feeling about this trade-off? Is it the data? Is it the architecture? Is it 50-50?
I told you that when you don't have input, you are dreaming, okay? You are sleeping and dreaming, okay? So.
But you had input before.
Right. Yeah. Yes. So right. So for us, input is paramount. Okay. So we work, and of course, the point is to assume the sensory and motor system. We don't work on it, okay? So because frankly we don't have to, okay? So you folks have done, many people in this room, so have done amazing work. So so we know so much about it. Not nearly enough, but a lot. Okay, so.
So in terms of what you might call memory in the mapping, this notion of plasticity is the only mechanism.
The only mechanism.
What would you take as our next cut at accounting for things like lifelong memory?
Yeah.
That might not be based just on synaptic variation that persists for that.
It will be, I don't know. There is, I don't know much else. There is synaptic variation, and there is death and creation of synapses and neurons, and what else? How else does the brain change? There could be sort of chemical gradients. There could be other things. So again. So, my attitude, these are all fantastic questions. My attitude is, I want to first find something for which this doesn't work, okay? And then sort of, I'll sit and think. Thanks.
So, in artificial neural networks, there is this issue that people talk about, which is catastrophic forgetting.
Yeah.
Which is,
Yeah.
very problem that you
Yeah,
have
yeah,
to keep
yeah.
running the data set
yeah.
repeatedly.
In a different life, I'm working on that. Yeah. So yes.
So in your model, and you explored that issue.
I mean, there is capacity to how much you can learn. Okay. And after that, sort of, you have to, if you exceed the capacity, your assembly started becoming, also, not only that, I mean, not only that, but there is homeostasis, and this means that the synaptic weights slowly decrease. So if you never use a word, not even in your sleep, sort of, this word will be forgotten, okay? Sorry.
Yeah, so when you said capacity, I mean, is there, I was trying, like, the early part, there was some part of it which made me think of Hopfield nets.
Yeah.
And like a
Yeah.
fancy
So it's very different, yeah. But
Hopfield nets
have capacity. Yeah. So this one have slightly better capacity, but not much. So I mean, we know that if you have a small language organ and a lexicon and you remember more words than it can, so you start forgetting.
Have you proven any theorems about this model?
For the first 8 years, we only proved theorems. Okay, so all these things all these behaviors that I told you, there are theorems. Okay, so just to say one, because I know that you and I like proofs. Basically, GNP is sort of enables theorems. Okay, that basically, I tell my students that take G0100. Okay, so 100 nodes, 1%. Okay, generated. I've never seen this graph before. Obviously, nobody has ever seen this graph, but I know so much about it. Okay, I know its color number, its click number, sort of its diameter, its what I'm saying, its independent set. So I know everything. Okay, so this kind of randomness is invigorating, or is mathematically invigorating. Doris.
People talk about this language of thought that even animals don't have.
Now you'll get me into trouble.
Do you feel like this structure is something that all animal brains should have discovered, and the difference between us and animals is like something?
I mean, that's a great question. Okay, it's like everything; it's a matter of semantics. Okay, I'm most comfortable when we don't call birdsong language. We don't, of course, signing is language, definitely. Okay, but or whale signals language. Okay, so and the reason is that it can be a little disoriented. Okay, so let's talk about language is human language. Okay, and let's by default sort of support the thesis, the exclusivity thesis that only we have language. And in some quantitative sense, okay, even if whales have a very developed language, which I believe they do, okay, if they communicate sort of in a very effective way, they haven't written our Hamlet yet, okay, so let's call language what we do. But language of thought is a different matter, okay, and there are people usually of the Chomskyan persuasion who believe that language as a communication is like a killer app and afterthought, okay. That originally the purpose of language is essentially to think. I go further, okay? In my opinion, the big first application of language was autobiography. Okay, so that basically, who am I? Where am I going? What happened to me? Where am I coming from? Okay, and full of hope and fear and nostalgia. Okay. Very emotionally laden. Okay, and this, even if I don't speak, is a tremendous advantage. Okay, it allows me to plan. Okay, so plan my life, and this is something it allows me to remember past experiences, or in ways that are other than sort of, synaptic in the muscles. Okay, if a little tribe got this gift, they will conquer all of Africa. Okay, you know what I'm saying? And then many hundreds of thousands of years later, they would speak also.
Episodic memory.
Episodic. Animals have good episodic memory. Animals have as good a hippocampus as we do. But but this is a different kind of episodic memory. It's episodic memory that then projects into an area where hierarchies are formed. Okay, now that I have the very patient people staying with me, okay, I can tell you that I believe that the biggest language feat that humans have, is not that they speak and communicate and they remember and remember stories and all that. It's the fact that we have this huge and very fast. So everything. So everything we say, I'm convinced, we have said before. A lot of our speech is fetched. Okay, where is this? How is it stored? As fast as we speak, we also there is a mechanism for storing these hierarchies. Okay, and this I think this I don't know how to do. I have no idea how humans do it. Okay, there is a fiber here called arcuate fasciculum, which is like all mammals have it, but in us it's much larger. And on the left hemisphere, for right-handed people, is 3 times bigger than the right hemisphere. And and I'm convinced that that's where this is where this bus for storing information is.
So I want to understand a bit the details of the experiment you mentioned at the end.
Yeah.
So I want to understand what is the training that does to you, and also it seems like you have already allocated areas for vision, for forming.
Yeah. Okay.
And now you created. What did you create?
Okay. So I'll tell you the experiment in detail. Okay. So thanks. Great to see you guys. So I can I'm not taking offense if people leave. Okay. So here's the experiment. So we start with we decide on the size of the now we can go of the lexicon. We now can go up to 10 nouns and 10 verbs. Okay. Otherwise it takes too long. Okay. And then what we do is we read it something like 5 times this 20 complete sentences.
So like, do you part of the affect area and the vision area while you're doing that?
Exactly. Okay, so basically when we say dogs run, okay, in the context areas, okay, there is a vision of dogs running. There is vision of dogs. There is mirror cells of the running action, sort of what you do when you run, and then there are other things. Okay, so there are various other things. We don't give names to the other areas. Okay, but there are assemblies that in most of the areas. Okay, and these are projected together in the symbol, in the lexicon. Okay, and that's the nascent assembly has already some connections. Okay, in the second time that dogs run comes, okay, it will be maybe or dogs jump. There's going to be different ones, and maybe even the dog has a slightly different representation. Okay, so you allow that. We have some noise. We have some randomness, and slowly a stable assembly for representation of dog will be in the nouns. A stable representation of run will be in the verbs, and importantly, there will be no stable representation for run in the nouns. Okay, that's the key trick. Okay, that's the key trick we have to achieve, and we can do that. And we can do that, unfortunately, up to 20 words.
And if you give it in correct sentences, like cat, dog, and like...
Then the kid will become weird. Okay.
But the kid makes no actions, right? Like everything happens as a byproduct of...
Yes. Nothing. I mean, so the kid just listens and creates the same image that the tutor has in their brain. Do that make sense?
Yeah, it's a byproduct without any usefulness for something downstream for the kid.
Oh yes, I mean, in the end, when the kid sees dog runs, he will say the dog runs.
Sure, but you don't reward the kid for like...
No. Listen, I mean, language is its own reward. Okay, so we get showers of dopamine when we speak, when we learn how to speak, and so on. Okay, so it's this is, I mean, there are experiments where you play to kids a recording of industrial noises, jungle noises, wave noises, and a person whispering, and they only listen to a whisper, nothing else. Okay, so I mean, they get a lot of pleasure.
I guess I'm saying in your experiment you don't have a penalization or anything. It doesn't
No. There is no reward. Yeah. Great questions.
I think so we should call a conclusion at this time. So let's thank Christos again.
Thank you very much.